Welcome everyone to my talk about our paper towards software-centric Listen Before Talk on software-defined radios. My name is Sebastian Bräuer, and this is a collaboration together with my colleagues Anatolij, Zubow and Falko Dressler. We are all from the TKN research group at TU Berlin. So let's start with software-defined radios. What is a software-defined radio? A simple definition might be a radio that exposes a direct interface to the physical layer through software. Why do we want that? It makes a versatile research tool, so it allows for fast prototyping, it avoids vendor lock-in, specialized use cases, and you can easily expand functionality. So, a typical SDR is structured in this threefold way. So you have a radio front end with a ADC and DAC chip, which then connects to a digital front end, which is usually an FPGA that does up and down conversion, and then you have some kind of link transporting baseband samples to the general purpose processing unit, or sometimes called host. So this structure also introduces some inherent challenges. So a big problem is the link from the host to the FPGA, because it significantly increases the RX-TX turnaround time. So for example, for USRP X310, this was measured to be 79 microseconds. And for modern protocols like TE-LA or 802.11, you want something much below 10 microseconds. So, what can you do? You cannot use these protocols on software-defined radios, and because you cannot use time-sensitive radio functions. So, there are some workarounds to this problem. For example, you can use the LTE-LAA testbed from National Instruments, or you can use Open Wi-Fi. And what they do is they implement most of the MAC layer functions directly on the FPGA. This works, but also violates the SDR paradigm. You end up with an SDR that's basically fixed in its function. You cannot do anything during runtime. And making changes to a protocol becomes significantly harder because you have to implement all those changes in hardware. So we thought we can do better. Our goal in this work was to preserve the access to the baseband and to push as much functionality as possible into the software domain. So only time-critical functions should remain in hardware, and also in a way that allows for time-slotted medium access for protocols like LTE-LAA, which require that. So our design idea was something like this. We implement a new component on the digital front end. We call it the LVT controller, and what it does is very simple. If you start a transmission burst from the host, the LVT controller starts a CSMA procedure, but while this is going on, the transmission is simply blocked, so it actually acts like a sample gate, and as soon as this the channel becomes available, you open the sample gate, you access the channel, and of course you need a way to tell the host, okay, you got channel access now, and this happens via a separate control channel. So we were testing this with LTE-LAA, so I will give you a quick refresher on how LAA works. So LTE-LAA is License Assistance Access, so LTE in the unlicensed spectrum. So it needs LVT. And for LAA, the channel is also still chunked into 1 millisecond time slots called subframes. And one superframe consists of 8 subframes. And before transmitting, a CSMA procedure must be followed. Very similar to 802.11. But the big difference is the transmission must start at a subframe boundary, so you need time-scheduled access. In order to achieve that, you are allowed to transmit arbitrary reservation signals that hold the channel until the slot boundary. So with our design, you can facilitate downlink channel access like shown here in this figure. You simply schedule a subframe for the subframe boundary. Then shortly after check were you able to access the channel, and if not, okay, you repeat the subframe, and in the meantime, if in the meantime the channel gets available, then this partial subframe acts as a reservation signal, and you can perfectly access the channel. So we wanted to implement this on a prototype, which we based on USRP X310 as our SDR platform, and we used the very popular SAS LTE software as an LTE stack. Our LVT controller itself is built as an RF NOC block. So what does this mean? RF NOC is simply a framework which allows you to build concept function blocks on the FPGA, and they share a common interface to the so-called crossbar, which acts like a switchboard, and so you can connect these function blocks at runtime. So you provide them at compile time, but you can interconnect them freely at runtime. So basically, the FPGA behaves like a flow graph in a radio, and there are some special blocks. So you have the radio block, which acts as your stream sink. You have the DMA FIFO, which is a stream source that basically buffers samples from the host. And then you have the DDC and DUC block, which are special blocks for up and down sampling from and to the USRP clock rates. With our LVT controller in the middle, this then looks like something like this. You have this LVT controller block which needs access to a separate radio and is connected directly to the DDC and DUC blocks. So we wanted to evaluate this also to see how much what gain on latency can we actually achieve. So what we did was we set up a signal generator to produce noise periodically with gaps in between, and then started our prototype with a 1 MHz offset so we can actually see where we're transmitting. And then, of course, observe the spectrum on a second USRP. So this then looks something like this. You see on the one side the downlink, and on the right side you see this interference signal slightly offset, and if we zoom in you can see the gaps which we then can use to measure the the RX turnaround time, RXT's turnaround time. So what was the result? It's terrible, really, really terrible. We achieved turnaround times from 100 microseconds to 155 microseconds, which were consistent within one measurement run, but random across multiple runs, which we at first couldn't explain. So we did a little investigation and found the following problems. The first big problem is the crossbar in RF NOC is actually not a switchboard, it's more router. You have packets, you transmit packets from block to block, and so every block in the flow graph adds significant buffering delay. And the second problem is the FPGA itself is deterministic, so you wouldn't expect any randomness there, but the CPU is not. And the USRP driver must start the receive and transmit streams, which you saw in the previous flow graph, and this offset is non-deterministic between those the start of those streams, but they are forced to synchronize in the LVT block, because they combine there, and depending on on which offset you got when starting the streams, you get 0 to 44 microseconds of added latency on top. But fortunately, these are software problems on an SDR, so we can fix them. The first thing we did was synchronize the start of the transmit and receive streams, and this totally annihilates this the added latency from the randomness, and then drastically reduce the packet size. So we measured again, and what we got was 90 microseconds consistently, which is very good, but not good enough. So as I said earlier, we would aim for 10 microseconds or even much less, preferably. So what will happen if you use this such a system in, for example, with a neighboring Wi-Fi node? If you have a non-standard delay, you get added collisions because you will access the channel and not notice that somebody else accessed this channel first, as you can see here in figure 5. And so we were interested in like, what is the actual impact of our prototype with competing Wi-Fi nodes? Is it actually that bad? So we want to measure throughput in a simple scenario, just one eNode B with a second AP, and see, okay, how much do they affect each other. The problem here is that if you measure this, then you need a receiver at both ends. And we currently have no LTE capable receiver at our disposal, and SAS LTE doesn't support this feature, but we need the receiver acknowledgements to adjust the contention window on the LAA side. So we came up with the very pragmatic solutions. We just simply split the antenna ports of the eNode B and AP in two via an RF splitter, and we connect them via cable to a third monitor in USLP, and the other end to a regular antenna, for which you then need port isolation. And then so the monitor can observe the transmission separately. And as you can see here, then we just use this monitor to notify the eNode B about any collisions observed, which is fine for this simple scenario. So what were the results? Pretty good, actually. So as you can see here, on the left you can see the throughput in megabits per second for the access point. So this was 802.11n, by the way, and in the middle is the throughput for the eNode B. This actually, the eNode B actually suffered a lot from this, as you've seen in the previous picture. The eNode B has also less opportunities for channel access due to the RX delay, which doesn't result in collisions, but just a bias against the eNode B. And on the right you see our measurement for just another access point, so a simple access point to access point scenario, which is about the same with more variance. We measured for a short duration. So this is, in conclusion, so we represent a new approach for listen before talk on software-defined radios, and this just serves as a proof of concept that an LTE-enabled eNode B running on an X310 using SALTE can work. And compared to a software-only listen before talk approach on SDRs, we reduced the turnaround time by 4 down to 19 microseconds. While preserving access to the baseband. Further improvements of this prototype are needed, but they are totally feasible. So there are ways in which you could feasibly improve this turnaround time. So thank you for your attention. Feel free to check out our source code, and I will see you in the discussions.